Okay, so I have a rod here. It's subjected to 3 different forces now. Okay, and it's going to create all kinds of different stresses. And I'm just trying to find, let's just find the stress at A. Okay, and then go ahead and draw that on an element, and I'll show you what that looks like when we're all finished here. Okay, so here's what we're going to do. The first thing I'm going to do is I'm going to make a cut, right? Because I have to figure out what the stresses are at point A there, or what the loads are at point A. So I'm going to make a cut to figure those out. And again, just from the what's the word I'm looking for? Uh, Static equilibrium equations. I know I'm going to have 600 pounds straight down, right? 500 pounds in the positive x direction, just to balance all these forces, and then 800 pounds in this direction, right? Now, the moments will look a little bit different, so, and I'll just go ahead and I'm going to sum the moments about that cut point there, right? And I'm going to have a moment about x, moment about y, moment about z. I should put in ijk onto all these. And then I'm going to have the moment created by all those forces. All those forces are at the same location, so the R is going to be the same for each one. So my R, again, from the cut to the forces, I go in the X direction, I go 12 inches, so 12I, and then 8 in the J direction, plus 8J. Okay, and I'm going to cross that with all those forces that are occurring over there, which again is going to be negative 500I and 800J and 600K. Okay, and that's the forces. So it's going to be all of those. Now, uh, you can trust me on this. When I do this cross product, I get 4,800 in the I direction. These are moments. Minus 7,200 in the J direction. Plus 13,600 in the K direction. Okay. Now this is occurring on that back surface of that, right? Because I make the cut and I'm just looking at the front part of that angled piece there. Okay, so if I flip this around and I look at that surface over here, okay, I'm actually going to have A over on this side again, because I'm basically looking. So if I'm looking down on the back side of that beam where I cut it, because that's the surface that I'm exposing all the forces on. Okay. Oh, excuse me. Of course, I do it wrong. Okay. Again, I flip it around, and A will actually be over on this side, right? That's point A over there. Okay, because again, I flipped it around. Okay, my x-axis goes off in this direction. My z-axis goes straight up. Okay, so from this, again, my forces, I have a 600 shear straight down. Okay, and I have a 500 in the x direction, like so. Again, remember I'm looking at the back of this, okay, as I look down. Okay, so now to balance the y, the torque that I've got around the y axis, okay, my y axis as I look down is actually coming, I'm looking in the direction of the y axis, right? I'm looking down the y axis, right? Okay, so a negative torque will be in this direction. That's the 7,200. Okay, will be in that direction. Okay, I'm not going to draw it gets a little tricky on, well, maybe I can go ahead. So about the x-axis, we'll see how I can do. Okay, so I'm going to have a moment in that direction. That's going to be the 4,800, kind of bending down like that. Okay, and then about the positive z-axis, I've got like that. Oops. Yeah. Actually, never mind. I think what I'll do here is we'll talk about those as we get to them. But I do have a moment about the x-axis and the z-axis, and we'll get to those in just a second. I think it's easier to talk about those in terms of, um, how we're when we get to them, okay? Which I suppose we're going to get to right now, because again, now the thing I want to find at A is I want to find uh, the sigma, okay, the normal stress, okay, and that consists of the normal force over the area plus mc over I, okay? So for us at this point, this is going to be in tension, right? So the normal stress, that's at 800 pounds in the y direction, that's going to cause it to be in tension, right? So in tension, it's going to be positive. So N is going to equal 800, okay? And the area, this is the area of a circle, is just going to be pi over 4 with a diameter of 2, okay? And that's positive because it's in tension. I've got a tension with regards to the normal force. Now, I also have a bending moment. Now, the bending moment about the y-axis, okay, that's the 720, that's at the neutral axis, right? So A is at the neutral axis there when I bend about, excuse me, the x-axis. Excuse me, that's the 4800 x-axis, okay? Um, so about that x-axis, A is at the neutral axis, so it has to be 0, okay? Now about the z-axis, if I think about how that going, and that's going to be created by this 800-pound force here, that's creating the 3,600 or 13,600 pound-inch moment. That's also going to be in tension as I think about how that rotates about the z-axis. Okay, so I think it's easier to visualize how that's going to rotate, causing A to be in tension. Because it's in tension, I'm going to add to it. So it's going to be plus that 13,600 times c, which is going to be the radius, which is 1, all over I, which for a circle is pi over 4 times the radius to the 4th. Okay, so these are both in tension due to the 800 causing tension, also due to that 13,600, which is the 800 times 12, causing A to elongate, be in tension. Since they're both in tension, I add them together, and I get a total normal stress of a positive in tension 17.6 KSI. Let me start drawing this element. So if I'm going to look at an element, and I will draw it, I guess, right here. Right, so there's my little element A. So again, now this is going to be in tension, meaning in this direction, it's going to be pulled, and it's going to be 17.6 KSI like that. Okay, so if I draw that element A, it's going to be in that direction. Now, the shear stress are a little bit trickier to kind of figure out what direction everything is going in, okay? First thing I'm going to talk about is in the x direction, right? So if I could think about tau in the x direction, okay? Well, that tau in the x direction, okay? Okay, tau is Tc over J plus Vq over It, right? Those are the two things that contribute to the shear stress. Now, the shear stress due to torque is actually at this point going to be, okay, to balance that, it's going to be downward. Again, because I'm looking at the back side of that. That 600 times 12, which is the 7,200, is causing that twist about the y-axis at A. Okay, and to balance that on, again, looking at the back side of that, that shear stress is going to be down like that. So it's not in the x-axis at all. So this guy goes to 0. Okay. Now the other thing here is I do have in the x direction, I have a shear in 500. However, in the x direction, it's at the edge. Again, the shear stress at the edge is 0 because Q is going to go to 0. So the shear stress in the x direction is 0, so that's pretty straightforward and simple, I hope. Now, things get a little trickier when I talk about Z. Now, with Z, it's still TC over J, and we just talked about this. The torque is going to cause a downward in the Z direction. Okay, so I'll throw the negative 7,200 times C, which is I, all over J, which is pi over 2 C to the fourth, where C is, again, 1, which is the radius to the fourth. Okay, so that's the torque due to torsion, or the shear stress due to torsion that I've got there. Now I've also got 600, and now this guy is occurring at the neutral axis, right? So I'm just looking at the semicircle above that to figure this guy out, okay? It's also acting downward, though, so I'll say minus, because it's acting downward. Again, that force is 600 pounds, V. Q, again, is going to be the location of the centroid, which for a semicircle is 4r over 3 pi. Okay, and then that area is going to be pi over 2 times the radius squared. Okay, so again, that's VQ, right? Because this is y bar prime, this is a prime, okay, which is Q. I, for a circle, is pi over 4 r to the fourth. And then T is the thickness, which at this point will just be the diameter of 2. Okay, these are both going down, so that shear stress is going down at this surface. Okay, and again, remember, this is on the back side of that. So when I draw this, it'll hopefully make sense. And that TZ then equals 4.84 KSI. So going and drawing this, again, on the back side, it's down. That means on the front side of this element, it is up. Okay? Because again, I have to balance that, for example, that 600, which is up. On the back side of that, it's down. So on the front side, it has to be up. And then I have the corresponding transverse shear along the length to help balance that in that direction. So again, much more interested in drawing, understanding what direction things are than if you get positives and negatives, right? Again, tension and compression is usually a bit easier to visualize. The shear stress, again, remember, I'm looking on the back side of that. So when I'm talking about things going down, okay, I'm talking about down on the back side. So on the front side, again, because I have to balance that, keep it in static equilibrium, it's upward. So that is what the element will look at. That's what those values will equal. And you just basically have to add together both components that create normal stress and shear stress to figure this stuff out.